Uh, Hello, everyone. Welcome to the TCS seminar at Jagiellonian University. This week, we will have the pleasure of listening to Gábor Tardos. Please show up in the camera. Gábor is famous for his numerous work in combinatorics and computer science. He received the Gödel Prize and other numerous awards. And today he will tell us about 0-1 matrices and
acyclic patterns.
Acyclic patterns. Acyclic patterns or acyclic patterns in 0-1 matrices. So, please.
Thank you very much. And it's great to be here, actually. It's a very nice, friendly place. And also the city is very nice. I've never been here. So, yeah, so this is a result that I will speak about that's joined with Seth Petty, and I presented it at the SODA conference this year. And okay, so maybe I should write something. And I have nice slides and everything for that presentation. But I mean, if other people give the talks, I prefer Blackboard talks. And so this is an experiment. Maybe nothing will be. So my handwriting is not very good. If you can't read something, then let me know and I repeat it, or maybe write it in better letters. Anyway, I think it may be a more informal talk if I don't present with slides. So this is an experiment. We will see how it goes. So the topic is extremal theory of 0-1 matrices. So I tell you what the problem is. So extremal theory, think about a Turan type extremal graph theory. You have a forbidden graph for a triangle, and you look for how many edges a graph can have if it doesn't have that forbidden subgraph. And that has a much longer history than the same problem for 0-1 matrices. So 0-1 matrix is just a 0-1 matrix with all entries 0 and 1. And I have to define containment. So this is the pattern P. It's contained in another pattern M. If so, this is a A by L pattern. Then this means that M has a A by L submatrix that is well, not exactly P, and it's bigger than P, meaning that for every place where P has a 1, it also has a 1. Every place where P has a 0, M can also have a 1. So that's really very close to graph containment, or as a subgraph. If you consider these 0-1 matrices as adjacency matrices, then this is a bipartite graph. This is another bipartite graph. Removing rows or columns is just removing vertices from the graph. And turning a 1 into a 0 is removing edges. So what you are left with is a subgraph. So if you consider these as adjacency matrices, then this is subgraph containment. But it's still much more than subgraph containment, because a submatrix has a given order of the rows and a given order of the columns, and you cannot change that. So when you take a submatrix, you can leave out rows and columns, but you cannot change the order of the remaining rows and columns. So it's like an ordered version of the bipartite ordered and bipartite subgraph. Statement. And so the question that we study is this extremal function x and p. So P is a 0, 1 matrix, that's the pattern. And this is defined to be max I write A norm. It's just the number of ones inside. So that's the one norm of this matrix you want. Such that A is an n by n 0, 1 matrix and P not contained in A. So that's the extremal function. It really corresponds to the graph extremal function. I give you how many vertices there are. So this is bipartite. I tell you that it's an n by n matrix. So there are n vertices on both sides. And then I count the number of edges, maximal number of edges that can be. So that's an ordered bipartite version of the extremal graph or Turan type extremal graph theory question. And because of this order, a lot of more nuanced questions can be asked than in the original theory. So, for example, this is how it started with a paper of Rényi and also, okay, so I have all the names here. Bienstock and Yuri. And so this is 90 and this is 91. And they basically proved, among other things, that this matrix, so I will just put dots instead of ones and leave empty space for zeros. That's very convenient for this containment thing. If you have a bigger matrix and you have somewhere these 4 dots, then it means that that matrix contains this. Okay, so the extremal function of n and this matrix is n log n. So we only consider order of magnitude. We don't care about constant factors. So this tells you exactly what the extremal function is. And this was used to find the maximum number of unit length diagonals of a convex n-gon. Not to find, but that's an upper bound. So n log n is an upper bound, and it was this easily implies that. I mean, you just take a convex n-gon, you make a bipartite graph from that. I mean, just putting in the unit length diagonals, and then you show basically that it doesn't contain this pattern. The ordering of the vertices is immediate because that's like a convex n-gon, so there is an order, right, on the vertices. And this kind of theory had this kind of so this is more of an example of this is how the whole thing started, and most of the applications is in 2 fields. Discrete geometry is one of them, so that's discrete geometry. And there are a lot of applications of this kind of extremal theory in algorithm running time estimates, because Okay, I don't want to go into that. I just want to say that this is an interesting topic. It has relations to extremal graph theory. It has also relations to the event Porchin-cell theory that I don't even tell you what it is, but if you know, then it's very closely related to that too. It's kind of common generalization of those two, if you want. And I want to tell you about some recent results in this field, and especially one very recent result. Okay, so there was a paper of Rényi and Final in '92 that said that, okay, this given these applications already, this is an interesting topic, so let's start to develop that as a research topic. And they did a very good work in formulating a lot of conjectures and proving a lot of results. And then nobody really worked on that for another more than 10 years. But now it's coming back to life. There are a lot of recent results. So that's the 0-1 matrix part of the title. The other part of the title was acyclic patterns. So this is an acyclic pattern in that if you consider that as an adjacency matrix of a graph, then the graph is free in the path in this case. But there is no cycles in that graph. And that's where bulk of the research is done, but not exclusively. So there is a even more recent result than ours from where is it? Yeah. Janzer. No. Yupu. That's just an example of a result about non-acyclic patterns. So this result says that the extremal function of P of N and P is, well, N to the 2 minus 1 over T plus little o of 1 if at most P ones in each row of P. That's a very recent result, and I consider it very nice. It's kind of a generalization of the corresponding two-run type extremal graph theory result, where the excluded matrix is a bipartite. Excluded graph is a bipartite graph, and on one side of the bipartition, every degree is at most T. And there, the extremal function is order of n to the 2 minus 1 over T. So this is much more general in the sense that you kind of forbid this graph in just one particular order. So the order is a big restriction. So proving anything is more challenging, and it's a little bit weaker because it's not all constant times this, but there is an n to the little of 1 error term here. But it's very close to that result. Okay, so that will be the exception that I mentioned. And most of the research focused on acyclic patterns. All these applications that I mentioned in database analysis and discrete geometry are for acyclic patterns. So here is a few conjectures about acyclic patterns, that the extremal function should always be like n log n. So there is this Rényi paper. It's full of conjectures, and it really helped my whole career because I was working on those conjectures. could prove or disprove some of them. And one of the conjectures said that X and P is order of n log n if P is acyclic. And so we were working on this conjecture with János Bach, and we found it, well, too strong. We couldn't prove it for even very small patterns, but we could prove something a little bit weaker for many small patterns. And so János Bach and me, and we conjecture that, well, this looks too strong, but how about order of n to the polylog n? So maybe some polylog depending on the acyclic pattern. And we conjecture that in particular because for most small patterns we could actually prove this. And well, maybe that's not the case, then order of n to the 1 plus little o of 1. Maybe that should be true for all the cyclic patterns. So all of this is wide open, except for the first one. So all three conjectures are for a cyclic one. And later, this first one was proved to be false. Okay, I use that one, so I go here. So prove that there is an acyclic such that the extremal function of that acyclic pattern is not n log n, but bigger than n log n log n. Well, it doesn't disprove either of our two conjectures, but it disproves the strong one. I mean, it's not my words, I wouldn't say such a thing, but Patty wrote it in the new paper that, well, this disproves the conjecture in its letter, it doesn't prove it in it, doesn't disprove it in its spirit or something. So clearly this is, well, not much of an improvement. And then there was, so I'm still on the history of things. My plan is to give detailed proofs, so don't give up. There was a result of Park and Shi. Where they improved on Patty's result, and they proved that it's at least, for some other pattern, it's at least n log n, log n, log n. And they could go on, so they could iterate this. And the result that I want to tell you about is, so it's Patty and myself, and it says that there existed a cyclic pattern such that X and P is omega n times log to the Cn for every C. So this is a construction that shows that this particular conjecture is tight. If if true. So for any polylog, you can go as high as polylog. On the other direction, even this n to the 1 plus little o 1 is open. The biggest class of acyclic pattern that for which it is proven was proven by the itself common measure, and they proved that for the n plus little o 1 for a large class of acyclic patterns, but not for all. So just I won't mention this direction anymore, but I give you the smallest example where I have no idea. So it's called the pretzel, and it's this one. So it's a 4 by 4 matrix. Maybe it's better if I connect the one that are in the same row or in the same column. And then you see the pretzel structure. And this is a good notation because pattern is acyclic if this drawing is acyclic. So in this case, the drawing is just a pass, and the graph is also just a pass. This is the smallest one where we don't even know this weakest upper bound. So who knows? I think it's a very interesting conjecture. I mean, the still living version. So the first version is not living anymore, but these two are living. I would be very much interested in proving that. But right now, I will mostly speak about this upper bound and this lower bound and some related stuff. So let me say something about this particular pattern. So everything started with this pattern. It has an n log n extremal function. And both of the proofs that I plan to give you are based on how the extremal function of this pattern is proved. So we saw that the extremal function of that pattern is order of n log n. So it has two directions how to construct such an example. So you have to have an n by n matrix. You prove a lower bound by putting a lot of ones in this matrix without having this structure. And the way you do it, the simplest way you do it, is that you take this diagonal and then you shift the diagonal by 1, 2, 4, 8, 16, so powers of 2. You basically have log n diagonals. Each diagonal has basically n elements. So it's n times log n ones in this matrix. I mean, the last one might be less arbitrarily small, but everything else has at least n halves. So if you don't care about constant factors, then this is n log n. So n log n ones, and it doesn't contain this pattern. Why? Because let's try to find this pattern inside this matrix. So this 1 has to go to some 1, maybe this one here. Then there is a next one in the column. It can be any of these. But we know that this main diagonal, distance from the main diagonal will be at most half of the original distance, because these were powers of 2. So this is like distance 2 to the k from the main diagonal, and the next one is already 2 to the k minus 1. Similarly for this one, the first possible one is like half the distance to the main diagonal. So if you close this as a square or rectangle, then in the best possible case, the fourth vertex will be on the diagonal, or maybe if you chose a lower vertex here, then it will be already below the diagonal. So that's this here. It doesn't have to be 1, but to the right of it, there should be a 1, and there is nothing below this diagonal, that's 1. So it's not contained. So that's a very simple construction. I call it diagonal construction. And it would be nice to have a construction like that, or that gives you this type of lower bound for some other pattern, maybe. That's possible for some patterns. So diagonal construction is just, you give the shifts. You take the main diagonal and you shift it by some set of values. And then you hope that whatever you get is does not contain your pattern, and then how many shifts can you do? And how could this construction be simple? If P is like a simple matrix, this acyclic 0, 1 matrix is very simple, then that's also an advantage. So this is the matrix that we found, something like this. So it's kind of complicated. It's an acyclic matrix. All these columns comes alternating. So this one has a net 1 in the lower part, the next one in the upper part. But it's not the simplest possible, and the construction we came up with was not this diagonal construction, but a little bit more complicated construction. So you can ask whether this can be simplified, and I want to present a simplified result here. So you can simplify it in 2 directions. Either you keep this complicated matrix and change the construction to a simpler construction with just diagonals, or you change this matrix to a simpler matrix, namely this would be the simplest that's possible, a 2 by. So this kind of alternating matrix, it's well, as I draw it, a mirror image of the first and the last line of this. This is as simple as possible because, well, a 1 by n matrix, even if you put all ones there, it has a linear extremal function because it tells you that every row can have at least 10 ones. So altogether there can be 10 n ones. So 2 by n is like the simplest possible matrix. And the interesting observation that we made is that you can do one of these simplifications, either one, it's doable. You cannot do both. So I will present a construction that is for the simpler matrix, but it's not a diagonal construction. And I always also tell you why diagonal construction never work for any patterns of 2 by k patterns. Okay, so before I do that, I give you another construction that works for this particular pattern here. And this is how it works. Label rows, columns by 0, 1 to the k. So n is 2 to the k now. So you just use the binary expansion of the number of the index of the row and column. And so the matrix A is A x y, and A x y is 1 if and only if. So x and y are now binary strings. If x bigger than y and differs in 1 position. So you can see that this is the same construction as that in a sense. If you consider these numbers, then differing in 1 position means that their difference is a power of 2. But not every, it's like half of, well, I guess this construction, because the difference is 0 here, 1 here, 2, and so forth, and therefore it's not for that pattern, but for something like this. Doesn't matter. I mean, it's basically, of course, the extremal function of all the mirror images of the patterns is the same. So this construction is doesn't get the entire diagonals. But sometimes if you add 2 to the k to a number, then it's not just turning a 0 into a 1. It's like turning a 1 into a 0 and then changing something beforehand. So, but it's structurally easier to work with. And this is what we want to do. We want to, instead of n log n, we want n log squared n. So how do we do that? Of course, we want to allow 1 even if they differ in 2 positions. Then you get n log squared n. 3 positions, and it's n log cubed n. And well, it's almost good, except the first 150 versions of this idea that we tried resulted in matrices that not only contain this pattern or that pattern, but it actually contains a full submatrix of big size submatrix of just ones, full of ones. So if you have, so you fix B, that's in 0, 1 to the k, and then you take set x that differ from B in 1 position, and you move downwards, you change the 1 to a 0, and you take a y that the set of coordinates that differs from B in 1 position, but you change upwards, then these rows and these columns will form a complete graph, basically. I mean, every I mean, it will be a submatrix of just one, because any of you can get from this to this by changing two positions. So you have to be a bit more careful there. Okay. So the history page, and here is this one. So I give you the construction, and it will not be the best one, but later on we will improve on this, but will be a good one. So there will be three parameters, A, T, and M. And the rows are labeled by A to the MT times MT, M to the T. So this notation is all the numbers 1 through K. So this sequence of numbers of length M times T. So a string of that length from numbers 1 through K, followed by one number from 1 through M to the T. The columns are indexed by K to the MT times M times times so this notation should be all the integers between m plus 1 to 2m. All the integers between. So this will play the part of these binary strings. So it has it's a long binary string. It's not binary actually. Now you have a larger index set. And these will be the places where I want them to differ. So the trick is that I don't just tell them to differ instead of 1, they differ in T places. I tell them where they should differ. And that's part of the description of the column. And so for some technical reasons, I want the first difference to be in the first interval, the second difference being in the second interval, so they are separated. I mean, every time there is a 1, they correspond to T places where you change the string, and I want one change in the first M coordinates and another change in the second M coordinate, and so forth. So, okay, so again, you have this A, that's the matrix that I'm constructing, and it will be A X Y. So X is say C1, C, MT, and followed by this large value S, and Y is D1 to DMT followed by let's make it I1 to IT. So these will be the indexes where they should differ. And okay, so the definition is that AXY is 1 if and only, so it's 1 or 0. So I just have to tell you when it's 1. If di minus di equals S, if I equals ij for so it's one of these indices and it's 0 otherwise. So that's the construction. And there are two things to do with a construction like that. First thing is to check that it has a lot of ones. Hopefully it has many ones. And that depends on, of course, these parameters. So you have to set the parameters right. So T will be a parameter that basically tells you how many places you can change. So that will be the, hopefully at the end you have something like n times log n to the T ones. So the T is something that the adversary sets, but you can play with K and M. So again, if you forget about this last part, and you just work with these sequences of numbers, then they are basically produce a 1 if they differ in T positions. Every position where they differ by the same amount. And that amount is noted in the row, and where they differ is noted in the column. Okay, so that's the.
So you assume K to be M to the T?
K to be M to the T. K should be like, yeah, if it's M to the T is much bigger than K, then you lose a lot because they cannot differ by bigger than K. Yeah. So let's do that. Let's set the parameters right so that. Yeah. So for every I in MP, they are equal most of the time, and for the special coordinates, they differ by just the set amount, the same set amount, and that amount is noted in the row. Okay. So how many ones in this matrix? Okay, so how many ways you can set Ci and Di and S and everything? So you can set I1 through IT, and to the T different ways. Oh, before that, how big is this matrix? So the size of the matrix, it's an n by n matrix, where n is K to the MP times m to the T. So it's a square matrix. I was careful enough to put m to the T here so that it's a square matrix. And how many ones? So now we are trying to estimate the number of ones. So you can choose I1 through IT this many different ways. And then there are those coordinates that are not differ, you can choose them. So I is not in ij, then this gives you k to the mt minus t. There are mt minus t such coordinates where they should agree, and each of them you can choose k different ways. And then you can choose s. You can choose it m to the t different ways. And then you don't have that much a choice because this difference really reduces so it's basically you have I equals this set. You have, instead of k, you have k minus s choices. K minus s to the t. And you don't know what s is, so I lower bound it by k minus m to the t. And to make things simple, I'd say that k is like 2 m to the t. Then you have to, so this is like k to the t over 2 to the t. So you have k, so the number of ones is at least, you have k to k times k to the mt times over 2 to the t times m to the 2t, and that's n times m half to the t. So as long as m is around log n, and m half is also around log n, then this is what we want. Of course, m will not be log n, because this is basically m to the m. So now k is m to the t. So this is m to the t squared m. But you can set m approximately log n over some t squared log n, something like that. 2t squared, something like that. So if you don't care, t is a constant. If you don't care about t, then it's log n over log n. So you have n times log n over log n to the t. And that's exactly what I promised, because I promised any power of log. Of course, you go t1 higher, then this log problem will not show up. Or it will. Okay, so it has a lot of ones. Depending on t, it has some n times polylog n ones. And now I want to show that this particular pattern does not show up in this matrix. I don't tell you how many alternations, but with some number of alternations, depending only on t, it will not show up as a submatrix. Okay, so yeah. I started the talk with the request that you stop me. You never stopped me so far, so maybe this is a good time to repeat this. If you have any questions, if something is not readable, which is probably most of the things, or you don't understand something, just ask. I know that it's broadcasted on Zoom, but I assume that there aren't too many people there too, so each of you represent 10% of the audience, and I don't want to lose 10% of the audience. Okay. So So we have to look around in this matrix, how it looks like. So there is this, so this whole thing is the matrix A, and there is a 1 here. There is a 1 here at column, at row X and column Y. So let's so this column Y is something like, okay, let's make column X is something like C1 through CMT S. So it's a sequence of empty coordinates. Oh, and an important thing. I have to tell you how to order the rows and columns. I mean, the construction is only a construction if I'm telling you how to order the columns, and you order them lexicographically. That's the standard thing. I mean, for the columns, it's important that it is lexicographic according to this thing. It doesn't matter what you do with the rest. And for the rows, you can order them lexicographically according to this, or you can even order them according to this and don't care about this part at all, or either way it will work. Okay, so now we know what the order is, and this row will have a lot of ones, assuming, yeah. Now, there are special cases when it doesn't, but let's assume it has a lot of ones. Basically, for every, so this Y will be something like C1 through CMT with some places changed. So there are some minus S's some places. And then the index of the columns also tells you what those places are, I1, I2, I3. So basically, for any set of indices, you will have a 1 here, except maybe this minus C will be outside the range, it will be negative or something, but if you're lucky, then for every set of indices, you have a 1. And it's very easy to see that the order of these ones is the same as the order of these indices. So if there is another one here, then so maybe this is something with J1 through JT, then J1, JT has to be lexicographically bigger than this one in order for this to be on the right. And I really want to care about the other one. So I have a reference one here, and I'm caring about the other ones. Where are the other ones? And I want to know where it first differs from this coordinate, the coordinate of Y, and this coordinate, where do they first differ? And so it depends on where I's and the J's differ. So you have I1 through IT, and you have J1 through JP, and so maybe this is equal up to this point, and then there is U and JU is bigger than IU. That's a possibility. And then I claim that these and these, so these first coordinates. So remember the columns are ordered lexicograph. So it's for columns, it's important to order lexicographically according to these coordinates. And for and these coordinates are partitioned into T blocks of length ME. And in the first U minus 1 blocks, this and this will agree because both are computed from these C's, and in both cases you take minus S in the very same place. So these blocks will be the same. And the first difference is in the block U. And in the block U, the first difference is that you take minus S in a later position. Meaning that in the position where you took minus S here, you don't. So the first difference is at the position where you took minus S. The first difference between these two and these two is one of these T positions. So I draw it in a different way again. So now I don't call these C's, but you call these D1, dt, and this will be something like D1, D, and T. D1 through D, I, U minus 1, so it's the same up until a point. And then the next one is D, I, U plus S. I mean, here I deducted S, here I don't deduct S, and I don't care whatever is after that. Just interested in that this is how any further one should start. So there are T possibilities here, each describe an interval. So for each one in the matrix, I can build T intervals depending on the value of the U. So if the U is 1, then this first difference comes pretty early. So that means that there will be an interval very far. If T U is like 2, then there is no difference there, so it's closer to this one. But there is another interval here. So that's interval 1, that's interval 2, and there are T intervals. For any one, you can build these T intervals, and all the ones in the row are in these T intervals. Okay? So, yeah, I'm still about this pattern though. So, just considering one row is not enough. So I consider another row. And I want to have the same column Y here, but another one. So that's say X prime. And for this, you can also build these intervals. They will basically be the same place because these intervals were determined by how far they agree with these coordinates, and these coordinates are the same. This epsilon y is the same. And the last place or the first place where they will differ with a different S value. So these corresponded to some S, and this will correspond to some S prime bigger than S. So what happens is that this, how much you add in the first place where you change, will be bigger here. So that means that they are basically the same, but you add more, so you get a little bit to the right. So there is IT here, I2 here, I1 here. So these will not be overlapping at all. These will be disjoint intervals, and this IT will be still to the left of IT minus 1 here. So there is this clear alternating pattern here, and that is clear that you cannot put in this matrix if it's long enough, because, well, I mean, you start with these two, and these two were arbitrary in the same column. So you find the places where these two go. Then you have to find, so what I'm saying is that all these ones later on will have to go to different intervals. There cannot be two that go to the same interval, because there should be in between a one here, and there is not. So after a while you run out, and okay. So that's one proof of where is the theorem? Oh, here. That there exists an acyclic pattern for which you have n times polylog n extremal function. If you look at this pattern, then it's clear that, well, we don't know in general that this n times polylog n upper bound hold, but for these patterns it does hold, because there is a general rule that if you have the last column contain only one, then you can remove that column, and the extremal function, by inserting back the column, the extremal function just can only grow by a logarithmic factor. For example, this pattern here has a linear extremal function. If you put this here, then it's the famous n log n. So in some cases, it does grow by a log factor. So this has really n times poly log n upper bound, but the upper bound and lower bound for this pattern doesn't really match, because you have to, if you want to increase t, then you have to add two more dots, two more ones, two more columns here, because, well, if you add increase t by 1, then the number of intervals will increase by 2. So it doesn't match, and, well, as a stickler I wasn't satisfied with this. I wanted to make it really tight. So you can modify the construction. And you can say that, so this is how we modify it. The difference must be S if J is even, and say M to the T plus 1 minus S if I equals Ij and J is odd. So how much you deduct depends now on the parity of J. Sometimes it's S, sometimes it's basically minus S, so made positive. Here, the S prime is bigger than the S here. So that means that these intervals will be shifted alternatively left and right. So this will be shifted right, but this will be shifted left. Next one will shift it right, something like this. And you see that now basically half as long pattern is also not placeable here, because you want to start here, you have to start right away with the second interval because the first is not in a good place. Then you go here, but this is not good. You have to skip this. You have to go here. So for every step you do two, you get rid of two intervals. And now the number of logs will be the same. So the extremal function of this. Okay, so what we have here with these improved constructions, so PT is this pattern. Where the number of columns is like T plus 2. Then the extremal function of PT is between order of n log n to the t and constant times n times log n over log n to the t. So it's almost matching. I mean, the power of log is the same, but there's this log error. Okay, so at this point you should say that, yeah, that's good enough, that's close enough, but I wasn't saying that. I was saying that, well, which one is it then? And the answer is that this is the right answer. So it's that down. And that's in a whole different proof. That's an upper bound proof. And I don't think I have time for that. But it is interesting in some sense, not just because I really like finding the order of magnitude exactly and how nice that is, but none of the application is from construction. The only applications of this theory is from upper bounds. So this really is, so there, well, for t equals 1, it's n log n, but for t at least 2, this equality holds. So the smallest pattern for which we have something new is this pattern. And there the extremal function is n log squared n over log squared n. And that might be useful for something. I didn't quite figure out where to apply it yet, but I'm working on it, and there might be some discrete geometry applications for this. So this came from realizing that the construction looks very nice. It should be optimal, and we just have to prove it. And basically, so I also plan to give you that proof, but I won't because I don't have time. But if you have, okay, maybe I erased, but there was this first result ever in this area was this n log n result for P1. And how you do the upper bound there was very instructive of how to do the upper bound here. And of course, it was much more complicated. One more thing that I promised and that may still fit into my time is because Bartosz told me that I can use 90 minutes if I wish, so I will keep going for a while. No. But this is a good time to ask any questions, because the rest of the talk will be just a very simple proof that you have any diagonal construction matrix. Then it cannot have more than log n diagonals for any of these order of log n diagonals for any of these P, PT matrices. So any question about the result so far then? Okay. So that actually goes for not just this pattern, but for any pattern that is acyclic and 2 by any size. But let's just consider this PP pattern. And I want a diagonal construction, so I have the main diagonal of a matrix and some more diagonals shifted. And I want to include this such that maybe this is one diagonal, this is another diagonal, this is another diagonal. So I just want to find which diagonals to use, and then I take the column, look at where it intersects that diagonal, that's one, and where it intersects this diagonal, that's another one, and then take where these rows intersect those diagonals, and that's the pattern. So it looks like it always works, but no, it doesn't always work. There is something about this diagonal that has to be satisfied in order for this to be really the pattern PT. So the only thing that can go wrong is that if this diagonal comes too close, then this might be before this one. So it's not an alternating pattern anymore. So what I really want is just this distance, that this one should be right shifted from this one. That's not a big ask. Let's see what it means. So this distance will be, say, x. And that's, by the way, the difference between the shifts of these two diagonals. So x is the difference between these two. So that's x, and that's a diagonal. So this is also x. And what you have to have is that this distance, which is the distance between these two diagonals, should be bigger than x. So in order to be able to do that, the only thing you need to do is find, so what's the construction? The diagonal construction is you have S is the set of shifts. And find A1, A2, A, T in S such that A, so these are in order, and A2 minus A1 is less than A k plus 1 minus AK for every k bigger than 1. If you can satisfy this, then this pattern will show up. So how do you satisfy these? So obviously, you imagine these elements of S, the shifts on a line, and for A1 and A2, it's obviously good to take two consecutive ones, and then you just have to find T more that are like farther away. And you cannot do that if and only if the remaining ones are in T minus 1 intervals of length. So this length is like D, and these are intervals of length D. And there are only T minus 1 of them, then you cannot choose T more. So this is the only way you cannot do that. But if that's the case, that's good. Then you have two consecutive one, and with at most T minus 1 of this size intervals, you can cover all the shifts. Okay, so let's take the first interval that contains at least 3 elements. Then one of these consecutive, so one of these steps from between two consecutive elements will be less than d half. And if you cannot do the construction with these two to begin with, then you cover the rest of the ones with just t-1 intervals of this d prime less than d half length. And what does that tell you? It tells you that, well, you started maybe the first two ones that was ever in this line, and they had some distance. You skipped a few, but not too many. You just skip those that only contained at most two, so at most some constant number, 2t-2 were skipped, and you find two where the distance is d half. Then you could proceed, and you can only do that log n times. So at most 2 times t-1 times log n is the total number of positions, shifts that you have in this set. So this diagonal construction doesn't work for these patterns, but this almost diagonal-like construction did work. Okay. Thank you very much.